Well, hi, uh, everyone, for being here and to attend to my presentation that I'm doing on behalf of my group, including Maren Chapanchik, Javier Antelis, Anthony Metzacapa, Daniel Murphy, Claudia Moreno, and Michele Sanolin. And this is going to be a presentation focused on the detection side. In particular, we will be discussing uh, yeah, sorry, I think is,
Yeah, there we go. Just have to click this one.
okay. It's going to be a presentation focused on something that I think I don't need to emphasize too much on the high frequency feature, but this discussion is essentially focused on the G mode, or I would call that the high frequency feature, as Daniel did on his presentation earlier. Then this is a presentation that is based on a set of results that we obtained previously. Essentially, we have several papers on the literature. The first one being the first estimation of the high frequency feature slope on real interferometric noise. And the second was essentially the application of this method into a particular case that Daniel briefly discussed this morning, where we estimate the slope on the E series. I will talk about this later. On a core collapse supernovae gravitational wave signal, two-dimensional gravitational core collapse supernovae gravitational wave signal, varying the nuclear equation of state. Then by varying the nuclear equation of state, we estimate how was the variation in the slope, and actually we were able to determine how sensitive is the slope according to different variations in the nuclear equation of state. And this third paper that essentially collects all the suite of computational codes that we've been implementing in order to estimate the slope in real interferometric noise. So essentially, this is one of the plots that we present in our first paper, where we produce the slope for the Kuroda model. And these are some of the results. In blue, the estimations of the high frequency feature slope for different realizations of noise. So continue with our investigation. I will focus on the second paper, the paper that we wrote with Daniel last year, and we follow the E series. Well, I think you cannot see here, but all the signals that we used are collectively denominated as E series that are produced with the Chimera code, and we introduced 5 different nuclear equations of state. And at the top panel, you're seeing the different strain signals for every single nuclear equation of state. Middle panel, the estimated slope for the high frequency feature using our methodology. And bottom panel, the final results after injecting these signals into real interferometric noise using CWB. So in blue, we are presenting here the different estimations of the high frequency feature slope. In red, the estimated slope, while in black dashed line represents the noiseless case that corresponds essentially to the slope in absence of noise. Then this work produced, these plots. And then at the bottom panel, you're seeing the range of variability that we obtain estimating the slope in interferometric noise of the scientific run O3B of LBK detectors. And then we can see something interesting is that at 1 kiloparsec, this is for 5 kiloparsec, I think is not visible in the presentation, but this is 5 kiloparsecs and this is 10 kiloparsecs. Then at 1 kiloparsec, one thing that is highly interesting is that we can perceive that the slopes are grouped in two main clusters, the cluster SFHO and SFHX, that if you look at the bottom panel are represented by this gray band, and the other nuclear equations of state are grouped in this purple band. Then we have two different clusters associated to these estimations. And you can see that once we increase the galactic distance, then this differentiation that we can see at 1 kiloparsec tends to disappear. And at certain point, they merge into a single entity, and it's no longer possible to identify between the different nuclear equations of state. Then in this case, a natural question come up, and is it possible to distinguish between these different nuclear equations of state in real noise? And then using our previous results, we introduced this methodology consisting in a convolutional neural network that makes use of CWB reconstruct events and certain pre-processing of this data that is essentially the input of our convolutional neural model. And after several steps in the execution of the convolutional model, then we can classify this information into 5 different classes, every single class corresponding to a nuclear equation of state. In this case, DD2, FSU gold, IU, oh, sorry, I think this is wrong. It's IUFSU, SFHO, and SFHX. Then we are interested in determine if we can classify these nuclear equations of state using the slope of the high frequency feature, which is actually an interest problem, having in consideration that we are using the reconstruction of these different signals within LIGO noise. Then in order to perform this analysis, we use 2 different time windows within O3B data. These are 2 different time windows of 1 week. And then using these injections in these 2 different time windows, we proceed to analyze the data obtained in order to determine if we are able to discern between these 5 nuclear equations of state. In the process, we found that our data set, our detection data set, is highly unbalanced. This is a fact that actually was reported in Daniel's paper. The SFHO and SFHX nuclear equations of state reports more detections than compare with the other 3. Then this induced an unbalanced data set. And due to this fact, we introduced an SMOTE technique. It is a technique used in data analysis studies in order to make the unbalanced data set being a little bit more balanced, introducing synthetic samples within those families that are less representative, in this case, DD2, FSU gold, and IU FSU. Then we proceed, and sorry, these are the results of the implementation of our code. Then you're seeing at the top the confusion matrices for 1, 5, and 10 kiloparsecs. And bottom panel, you are seeing the rock curves for each model. And then we can see that the detections are nicely grouped along the main diagonal, making explicit that our methodology to identify and classify these nuclear equations of a state is working. As well, in the rock curves, we introduce also two different parameters in order to prove how well is the convolutional network estimating these different families, including the micro average and macro average rock under the curve. And the difference essentially between these two parameters is that the micro average assigns certain weights to each family depending on the number of instances in each family. And unlike the micro average, the macro is not assigning a special weight for each family. Instead, they assigns the same weight to every single family regarding the regardless the number of instances in the data set. So we can see that the classification is actually pretty good. What we can identify from 1 kiloparsec to 10 kiloparsecs is that the ability of our model is getting worse when the distance increases, which is natural due to the characteristics of the signals that we are dealing with. These are the results for the second time window that I'm calling it TW2. And as you can see, the results are pretty similar to the first results that I presented before. Still, the convolutional neural network is identifying very well the different families, being more representative on those nuclear equation of states that actually exhibits a larger number of terms. And these are the numerical results before and after the application of the smooth technique for the three galactic distances introduced in our analysis. We also present the area under the curve in the OVR stands for one versus the rest methodology. This consists in taking one family as the true family, while the remaining are considered as false. And in this case, the classification analysis becomes only a bilinear case where we are estimating only two families instead of five, like this case. And then we have a solid discrimination between the different nuclear equations of a state so far. And let me conclude with the following. We are enlarging our suite of computational methods to estimate and characterize the high frequency feature. At the first level, we have the estimation of the high frequency feature. Actually, we have now how the nuclear equation of a state is affected in terms of the high frequency feature. And now we have a classification method based on the classification of the slope of the high frequency feature, and then enlarging these computational tools. These enable the possibility to give a step forward in order to perform parameter estimation, astrophysical parameter estimation, using this set of computational tools within real noise. Another conclusion is that we have a solid method to classify it within real interferometric noise within the different nuclear equations of state. And this is important because using these estimations, we are able to produce new solid results in terms of how to use the high frequency feature slope estimation in terms of correlations with the astrophysical parameters of the source. And then I think this is all on my side. So thank you so much.
All right, we have plenty of time for questions. Thank you, Alejandro. So we've got one at the back and then we'll get to you next.
Thank you for the nice talk. So one question. So I understand that if you fix a progenitor and you change the equation of state, you're going to change the slope. But isn't the progenitor itself going to change the slope as well? Because the accretion rate is going to make the star grow larger in different time scales. Isn't it going to affect that and create a degeneracy with the equation of state in the slope?
Oh, we are not changing the progenitor. We remain a gravitational wave signal, and we change the nuclear equation associated to the signal, but not the progenitor itself.
Okay, so but the progenitor will likely introduce a degeneracy in the slope.
Yeah, that's correct.
Okay, thank you.
Pablo basically stole my question. I don't know which mass did you use?
Which one? Sorry.
What was the mass of the progenitor?
15 solar masses.
Okay, so it's quite smallish.
Yep.
But I think as well that if you tried a higher mass progenitor, then maybe you see the equation of state effects more because if they're closer to the maximum mass limit.
Oh, for sure. I mean, something that we need to do is to implement this methodology for different kind of progenitors, but this is a first step in that direction. So yeah, but for sure, I'm completely agreed with you. Yep.
Thank you.
Yep, thank you.
Got another question here, and then, well, I think we do have time for yours, so.
Thank you, Alejandro. My question is, you showed the plots where you can distinguish the slopes between the 5 different equations of state. And then here you have the one versus the rest. Did you investigate what happens if your network takes one versus the rest, says, hey, this is DD2, and then you do the same one versus the rest and says, hey, this is SFHO? Were you able to do any joint analysis, maybe like 2 versus the rest or something, to make those situations go away?
That's actually a very good question. We are working on it because we already have these computational tools to do the estimations. Now, the question is, can we use some a statistical method to associate to a correlation between the slope and a certain nuclear equation of state, meaning that consider particular core collapse supernovae gravitational wave signal. We can tell you what is the slope of this. Then you can think of what is the probability that given this slope, you can obtain certain nuclear equation of state. Yeah, we're working on it because we already have all the tools to do that. Then we are moving into the statistical analysis. So yeah, we not yet, but it will be done for sure. Yeah.
Hi, thank you for this wonderful talk. So looking at your ROC curve, it speaks very sharply in the starting stages. So I'm wondering, did you look into the data leakage or some probable biasness regarding your equation of state or not?
No, we don't. This data is essentially reported by CWB. We perform this CWB analysis, detection analysis, and then all the information is produced by analyzing the detection in the real noise. Yeah.
All right, thank you very much for all the questions. Let's thank Alejandro again.
Thank you.
We'll move on to the next session.